In Part 9, I mentioned how important the silicate degree is in regards to calculating the required flux constituents. In this presentation, I will be introducing the concept of the silicate degree and how it will be used in the calculations. However, I must revisit the concept of a base and an acid in regards to dry chemistry, then move on to the silicate degree, since both concepts coincide. I am Rob Boyko, Boyko Mineral Exploration, and welcome back. Wet chemistry refers to the reactions that take place using wet solutions. The reactions can either be two or more chemical solutions mixed together, or they may be two or more reactants that could be a dry compound or element and a chemical solution. In this simple example, listed as wet, sodium carbonate is added to sulfuric acid. The resulting reaction produces a product of sodium sulfate, which precipitates out as a solid, the expulsion of carbon dioxide gas, and the creation of water. What is noticeable is that the base, being sodium carbonate, is added to the sulfuric acid, and on the product side, the solid precipitate is a salt, carbon dioxide gas, and water. In wet chemistry, anytime you combine an acid with a base, the result will always be a salt and water, and depending on the reactants, a gas will be produced. In dry chemistry, the reactants are always a dry substance. That is to say, a compound or element in its solid state. In a previous presentation where I discussed the reagents or fluxes, silica as well as borax were shown to be the acidic fluxes and the sodium carbonate was the base. On examining the reaction equation under the dry heading, these two compounds will become fluid when melted. There is still a base reacting with an acid, which is the silica. The product becomes disodium silicon trioxide, which is the salt. The remaining product is the carbon dioxide gas, same as with the wet chemistry. One other thing to notice is the formula for the disodium silicon trioxide. It can be rewritten. In dry chemistry, in order to produce that ideal slag, the base metals must be converted to a single oxide. The sodium carbonate under fusion will reduce to a single compound of disodium oxide. The disodium oxide is in the required lowest oxygen state. The silicon dioxide is in its stable covalent state. During cooling, the two compounds will alloy together to form a sodium silicate. This would become the slag, a sodium silicate slag. The double dots signifies a double bond between the two compounds, meaning a fusion or alloying of the two compounds. Also notice that the base and acid relationship is still present. I briefly explained how the disodium silicon trioxide formula can be changed to show that the product during fusion will become a disodium oxide in its smallest oxygen state, fused with a silicon dioxide to form a sodium silicate slag. During fusion, any base oxide complex will reduce to a single metallic oxide. In many textbooks, you will see the term RO. R, in the formula's context, refers to the base metal, and the O represents the oxygen atom. As shown in the table, the lead oxide is just the sample used. However, it could be zinc, iron, aluminum, and so on. It is the ratio between the silicon dioxide's oxygen atom and the base metal's oxygen atom that determines the silicate degree. As shown in the table, in order to have a monosilicate slag, there would have to be two molecules of the lead oxide and one molecule of the silicon dioxide in order to have a ratio of 1:1. Lead oxide is the base metal in the example. In reference to a base and an acid, the lead oxide would be the base and the silicon dioxide is the acid. Therefore, 2 molecules of the lead oxide plus 1 molecule of the silicon dioxide is considered as having a monosilicate degree of 1 to 1. The monosilicate degree is applied to the neutral or high sulfide class 2 ores, or concentrates. The subsilicate degree is applied to that class 2 material that contains a lot of contaminants, whereas the bisilicate degree is applied to those acidic, neutral, or oxide ores, that is the class 1 and class 3 materials. The individual silicates of lead oxide and alkali metals are easily fusible. However, those that are of iron and manganese are a little bit more difficult to fuse. The individual silicates of calcium, magnesium, and aluminum will not fuse at the standard or ordinary assay furnace temperatures without adding a reagent that will act as a catalyst in order to reduce the fusion temperature. An acid in the correct concentration is still required. Silicon dioxide melts at 1750 degrees centigrade, borax at 752 degrees, and sodium carbonate at 852 degrees. You are now aware that the silicate degree is used to assist in the decompositions of the ore or concentrate. It allows, through calculation, the promotion of the slagging to collect the unwanted elements and impurities. It is also used to create a more fluid melt. It has also been learned scientifically that the silicon dioxide is to be replaced by the borax. It has been determined that the amount to be replaced is 1/3. The sodium carbonate is used, that is, added to the charge to promote a very fluid melt. Since the borax, even though it is an acidic flux, it is not the same as the silicon dioxide. The constants shown are used to determine how much borax will be needed. For the class 2 material, either the subsilicate or the monosilicate degrees are used to calculate the amount of silica required. Once that figure is determined, then 1/3 is replaced by the borax. Each item in the flux must be calculated to be able to create that ideal slag. This basic calculation is used in conjunction with the silicate degree. At first, in order to find the required moles, a balanced reaction equation must be written. The formula is simple math. I mentioned a while back in an earlier presentation to download a free copy of the periodic table, as well as investing in the purchase of the Audubon Field Guide to Rocks and Minerals. This little book can be purchased from any local bookstore. It is a popular book that is used as reference material by many geologists and mineral assayers, not to mention the everyday rockhound. A balanced equation is used to work out the number of moles of a substance. This calculation is used to calculate the amount of silica to be used for each element in the charge, being the sample as well as your flux material. The mole or moles refers to the number of molecules of the substance, and in this case, the silica. And the molecular weight refers to the weight of the single molecule of the silica. The denominator section of this calculation refers to the constituents of the ore or flux material. The molecular weight is determined from the periodic table of the elements, and the ore constituents that is, are found in the field guide. To demonstrate the use of the calculations, for simplicity of understanding, galena is used here as the example. Galena, using the Audubon Field Guide, is listed as lead sulfide or PBS. It will be assumed that there are no other constituents such as quartz and so on. The ore weight for the crucible will be 15 grams, which equates to 0.5 of an assay ton. This would be the average or suitable amount for an assay. The sodium carbonate added to the charge is always equal to the ore weight. Being a sulfide complex, the ore class is class 2. Assuming no other contaminants, the silicate degree is monosilicate. From the periodic table, the lead is 207.2 grams, the lead oxide is 223.2 grams, the lead sulfide is 239.3 grams, the silica 60.1, and the soda ash at 106. Each of these components and/or elements requires a certain amount of silica to form the slag. To start with, the base metal component is first calculated. As the lead sulfite reacts to reduce to lead oxide, the amount of silica required to slag the base metal oxide is shown. Since there is one molecule of silica having a molecular weight of 60.1 grams, it is divided by the two molecules of the lead sulfide times the weight of the ore material being 15 grams, gives us the estimated amount for the required silica as being 1.88 grams. The calculation is repeated for the litharge. Note here that the amount of the litharge is 60 grams for the charge. However, the amount of litharge required for the button is 30 grams. The 30 grams is used for the slag formation. Thus, for the calculation, only 30 grams is used in the calculation, which gives the estimated amount of 4.04 grams of silica required for the fusion of the lead oxide. The sodium carbonate is calculated in the same way, resulting in the estimated amount of silica to be 4.25 grams. The total required amount of silica is calculated by simply adding up the three results, giving a total of 10.17 grams of silica to be mixed with the ore. In order to lower the fusion temperature, 1/3 of the silica is replaced with the borax glass. The total amount of silica that was required was 10.17 grams. Since 1/3 is to be replaced, the actual amount of silica required is 6.8 grams. The amount of borax is calculated using the borax equivalent constant for the monosilicate slag, which is 1.3. The amount of silica being replaced is 3.39 grams. Therefore, 1.3 times the 3.39 gives the estimated amount of borax required as being 4.41 grams. This is added to the charge. Now that the quantities of material are known, a charge summary, that is the charge recipe, may now be documented. This is a very basic recipe. It, however, does not take into account the oxidizing or reducing power of the ore or flux material. This will be discussed in more detail in an upcoming presentation. Completely mixing and homogenizing the four flux materials with the ore prior to placing the mixture into a crucible should result in an ideal slag and lead button of approximately 28 to 30 grams. In this presentation, I elaborated on the silicate degree as well as the borax equivalent. I also, using a simple example for your understanding, I showed you how to use the simple calculations to determine the required amount of silica and borax. I introduced you to the ore weight and the soda ash quantities used. However, I did not elaborate, as this will be discussed in an upcoming presentation. With what I have discussed so far, you should have enough knowledge to create your own simple flux recipes. In a future presentation, I will be elaborating a little bit more to introduce the oxidizing and reducing potentials in the calculations. For now, the next presentation, as I have mentioned previously, will be a further discussion on determining what your ore concentrate constituents may be. I will further discuss the slag colors as well as the use of a process referred to as vanning. I will also discuss the use of a couple of acids and a base solution. As always, if you like this presentation or know of someone who may benefit from this information presented, do give it a thumbs up and a share. As for now, until next time, thank you for watching. I'm Rob Boyko, Boyko Mineral Exploration.